Thank you for attending to the last day of the conference. It's a great pleasure to introduce to you Professor Bruno Oliveira from here, University of Miami. He's going to speak to us about the geography of surface with big cotangent bundles and singularity invariants. Please, Bruno.
Thank you. Okay. Voice is strong, but still. Well, I'm thanking for inviting me, but I'm actually from here. So, my name is Bruno now, so I appreciate it, but I do appreciate it. Well, it's very nice. This talk is about the geography of surfaces with big cotangent bundles. So there are surfaces of general type, and the role played in understanding bigness by singularities. This is work of myself and of two of my past graduate students, Johannes Lasega and Michael Luis Weiss, and it's work in progress with Damien Broadbeck and Urban Russo. All right. So let's first take some definition. So the X for me will be a smooth projective manifold of dimension n. Later, most of the class will be, so the lectures will be of dimension 2 surfaces. And a big cotangent bundle means it's right here, means that basically the growth of the number of sections, the dimensional space of sections of the symmetric powers of cotangent bundle is as large as possible for that dimension. So it's like ample among the quantitative perspective, less from the qualitative perspective. So that's what big is. So there's plenty of symmetric differentials. This work actually of Campana and Pon shows that big cotangent bundle implies such the variety of type. Of course, for surfaces is of known long time ago. Just incidents could be described as a classification argument. So we know the types of surfaces and we could analyze them and show that the big cotangent bundle implies that the surface is of general type. Then let's try to see one application of big cotangent bundles towards hyperbolicity. So big cotangent bundle implies that you have 20 subsets, even if you ask them that they vanish on an ample divisor. And if I have a symmetric differential that vanishes on an ample divisor, that actually is imposing conditions on entire curves. Entire curve is a known constant holomorphic method from C to your variety, and W gives you an algebraic differential equation of the first order that F must satisfy. I mean, geometrically, it can be seen in the following way. So if I have symmetric differential, it defines in the projective cotangent bundle, defines me as an hypersurface. Here is here appears as this shape, and what I must have for my entire curve is that when the entire curve is lifted from variety 2 to projective extension bundle, then that lifting must lie on the zero locus of the stated with the symmetric differential. And that condition is called canonical vanishing. And so the more symmetric differentials I have, the more constraints I have on entire curves. And this is put into full practice. I mean, these ideas were incidents from Ferrier, from Bogomolov. We talk about mentors and Lashat. So Bogomolov is my mentor, and I guess he shares many properties with with attachments. Bold, I won't say the other ones, but they're the good properties that it shares with attachments. Anyway, the work of Fedia and later of Milan shows that if I have a surface, if you consider bundle, then that surface satisfies the famous Green-Griffith line conjecture that says that if I have object variety of general type, then there must be proper variety such that every entire curve must lie in that subvariety. So for example, for surface, it would imply that there are only, well, finally many rational curves on certain functional type and so on. So this is the conjecture. But if the conjecture model is big for surfaces, I have conjecture. So one.
Can you recall the definition of general type? Can you recall?
General type means that the canonical line bundle is big.
Lots of sections.
Lots of sections. It's like the. So it's the highest Kodaira dimension. So for surface, for curves, it's genus bigger or equal than 2.
Isn't there a definition that sort of fits this statement?
I mean, yes, I mean, if it's not a general type, then there will be entire curves. Well, there will be entire curves. You say that if it's not a general type, then there are entire curves. You could make arguments like that, but if it's not of entire curves, yeah, I mean, there is a relationship between, but that's a very sophisticated way to describe a general type. General type, which is a canonical line model, has plenty of sections. Out of it, there's plenty of sections. It's back from Kodaira dimension. So, okay, so semantic differentials can be used to prove the Green-Griffith line conjecture, but there are, it's known, we'll give an example now, or a result that you can have varieties of general type with no semantic differentials. So, therefore, if you want to use semantic differentials to prove Green-Griffith line conjecture, you won't be able to. So this notion of semantic differentials can be extended to KJ differentials, where when case 1 is the case of semantic differential. But in the past, it was very difficult to get a handle on. And now there's more technology, and so it's used, and there's several results. I'll mention some where the proof depends on KJ differential, not on semantic differentials, but it's not the topic of this lecture. So the questions, I'm going to give some questions that coming from hypersurfaces that motivated this work. But really the goal of this lecture is to talk about big cotangent bundle. So yes, big cotangent bundle has an impact on hypersurface questions, but I'm not actually focusing on that. I'm going to focus on understanding bigness in the surface case. So by the way, a conjecture, an hypersurface conjecture, very important in the 70s, is now pretty much solved. Is that the generic hypersurface in N, when N is the organic tree, and the hypersurface has to be bigger than 2N minus 1, then that hypersurface should not have any entire. All right, and the work of Milan, Maï, Altul, Pon, and many others prove the Kobayashi conjecture for very generic hypersurfaces whose degree is bigger than 80. Generic means you, on the parametric space of hypersurface, you take away count of the many varieties. And outside of that, any hypersurface over a point outside of that will be very generic and will satisfy the Kobayashi conjecture. If you want to do generic, Then there's an idea of SU, but it was a full proof of Damian Brockback in 2016 proved the generic case when degree is very large. So the degree plays a role. It's easy to prove for IDP because these proofs involve jet thresholds. You can show more abundance the highest degree.
What does very generic mean?
Very generic means, so you look at the parameter space, all hypersurfaces. Generic means you take away a proper subvariant. Very generic, you take away countably many subvariants. All right, so this is the kind of connection to hyperbolicity, but now we're going to start focusing on bigness. So first, let's talk about symmetric and genus. So you look at the dimensional space of symmetric differentials of a certain degree. Right? That quantity is a rational invariant. Right? And that implies that bigness is a rational invariant. Every variety which is rational to a variety will be constructed by a bundle. But an important property, perhaps essential, makes more interesting, is that bigness of cotangent bundle is not preserved under deformations. The bigness of the canonical line bundle is preserved under deformations, but the bigness of the cotangent bundle is not preserved under deformations. So now let's. So I'm coming to a motivating question for this work. Brookman in 71 explicitly showed that smooth hypersurfaces in Pn, when n is bigger than 3, don't have any symmetric differential. So, for example, if you wanted to prove the convection conjecture using symmetric differentials, you'll be doomed. There are no symmetric differentials on hypersurfaces, so you cannot use them to prove the convection conjecture or. And
what does that notation mean? GS.
It's this guy. It's the dimension of the space of symmetric differentials of degree m. So you show that I know symmetric differentials, but then the question it came was a question that was by failure, are there deformations? Can I deform a smooth hypersurface to a surface, smooth surface, which has big cotangent? So you have a family. The general member is a smooth hypersurface, so no symmetric differentials, but there's a special member with big cotangent. So abundance of symmetric differentials. So an example of if it is an example of the fact that the symmetric polygenia are not deformation are not preserved by deformations. And of course, then the question was that if you can do that, how low can you go on the degree? Right. So and with failure, we proved this in 2006 that indeed it's true that there are surfaces which are surfaces which are deformations of smooth hypersurface with many with big cotangent bundle. And they appear, you can see, they appear as resolutions of novel hypersurfaces in this. Then the question was, as we'll see, the logic. That's to do how many singularities we can have on a hypersurface of degree. Okay, so from now on, we are in the case of dimension 2. So perfect. So I want to understand bigness of cotangent bundle. So bigness is about dimension of the space of symmetric differentials. So of course the tool we should use is Riemann-Roch. Is a Rook version of it. And so if you use the Riemann-Roch plus Bogomol's vanishing, I want to show that second cohomology group for symmetric powers of cotangent bundle vanishes once the degree of the symmetric thresholds are bigger or equal than C, from stability arguments. So if you have that and you do the asymptotic Riemann rock, you get what I call H0 omega, which is the limit of the dimension of special section divided by m cubed. Is equal to the part that comes from the topological part of Riemann rock, which is the second number divided by C factorial. And then you have the plus, it's here, it's the asymptotic leading piece of the growth of H1 for symmetric powers of cotangent bundle. Okay, second number is C1 square minus C2. So this is what we have. Of course, from here, if I want to set bigness, you realize that if the second number is positive, then clearly this is going to be non-zero, and the cotangent bundle will be big. Right? So that's the first simple observation. And clearly use this to talk about the business of boundaries of rational curves with curves of such a type and C1 square with the second number here. Okay, so this is clear. Of course, we won't talk about classification, so I'm going to make some try to understand in the geography of sense of general type, which is which is basically looking at the pair of sharp numbers C1 square and C2, for which there are minimal circles of general type, and I want to understand that for that pair, can I find a circle of general type with a big cotangent bundle? So here it tells me that if I have C1 square over C2 bigger than 1, which is equivalent to second segregate number being bigger than 0, the surface necessarily has big cotangent bundle. So if that was it, the talk will be non-interesting. I just observe here that if you look at the second number of a surface of general type, that's going to be negative. Checking, because we know from Brookman that you have no symmetric differentials, so clearly cannot be big, and the second number cannot be positive. So this is just an observation here. Okay. So of course the question is, what can we say about bigness of cotangent bundle if I have my second number negative or equal to 0? Well, if you want to do that, I observe this. Okay, can you have the cotangent bundle big with the ratio is less than 1? Of course, it's not an interesting question if you allow non-minimal sums. Because if I have a surface of general type with big cotangent bundle, okay, with second number, so with second number positive, there's big cotangent bundle. Now, if I start blowing up, then the second number starts getting decreasing by 2. So if I blow up enough times, that I obtain a surface with big cotangent bundle, because the cotangent bundle is preserved. If I have a map, a dominant map from surface to another surface, and the base has big cotangent bundle, the top also has big cotangent bundle. So if I start blowing up, I can make the second number negative, and we'll have big cotangent bundle. So there's not an interesting question. So I really have to ask this question: it's only interesting if you only consider minimal surfaces. All right. So okay. So let's sit in here. So to do that, let's remember some things. So if I have a rational class of surfaces with general type, there are 2 important models. One is the minimal model, which is a smooth surface where the canonical bundle is math. Okay, that's obtained for a surface. It has -1 curves, then will not be the canonical bundle will not be number will not be left. So I'm supposed to blow down those -1 curves till I obtain a surface with no -1 curve, and that surface will have the canonical bundle of nerve and will be the smooth model. But if I want a stronger possibility of the canonical line bundle, if I want it to be ample, then I can do that. That's called the canonical model. But now the canonical model might have similarities, and we'll have any similarity, and that comes from we have a surface of a minimal surface of general type. Inside it, you'll have -2 curves. So these are smooth rational curves with some such -2. They come in configurations, connected configurations. This configuration is the configuration of the exceptional locus of AD singularity, and I can contract those -2 curves, obtain the singularities, and the terms obtained by contracting -2 curves is the canonical model. All right. So another thing. So if I have this X curved X is a rational class of surfaces. So I'm going to talk about what are the topological invariants of these. I'm going to set them to be the topological invariants for the minimum model, for the smooth one minimum model. In particular, so the C1 squared is of the minimum model, and the C2, the second set number, that is the second set number of the minimum. All right. So, and also, I'm going to say that the cotangent bundle of the rational class is big if there is a smooth model with big cotangent bundle. Make sense? Then I do the simple picture where it's the geography. Well, I have a plane where the coordinates are the second set number and the C1 squared, the second set number. And we know that in terms of general type, live in between two lines, or 3 lines, to consider this. So you have the Bogomolov-Yao line, where the slope of C1, this is at the slope of C1 squared over C2 is 3. There is no surfaces here. And then the bottom line is another line, and there's no surface, all surfaces of general type, minimum surface of general type, and they have C1 squared bigger or equal than 0, or bigger than 0, and they have C2 also bigger than 0. And so these are the two limiting lines. We notice now that above the slope 1, these are the surfaces here. They have second number positive, so they have by topological reasoning immediately be cotangent bundle. So the question is what happens below slope 1, and I put here slope 1/5 because it will play a conjecture role later on. So I want to know if I have some pair here, a pair of shell numbers in that point I just put there. Can I find a surface of general type with those shell numbers with the cotangent? That's the idea. All right. Is there any questions? So, if I want to do this, of course, I need to understand the other part of the asymptotic log. I obviously can understand if I know shell numbers, I know the second serial number, that's trivial thing. What I don't know is what is the leading coefficient of the asymptotic behavior of the growth of H1 of the symmetric powers of the cotangent bundle. That one it depends very much on the complex structure that you have on your manifold and varies under deformation. So it's not it's delicate, very delicate. So with the students we showed that this H1 omega, symptotic piece of a minimal surface, can be, it has two parts. One part, which is called the non-localized part, here is the definition, has to do, and for which I'm not going to say anything about in this talk. We know several type of results on this. It's kind of difficult to actually get any results on this, but I never focused my attention on it. So great, the definition is here, but let me focus on the other part. The other part is what we call localized H1. And that localized H1 comes from the similarities. Each similarity is a contribution to H1 omega, and that's the part I'm going to focus on. All right. And okay, so this is the surface invariant, and for which the definition is here. It has basically to do with it's the local growth of H1 of symmetric powers of the cotangent bound. All right, and so this is the event that we would like to understand. So what we got here is, of course, I mean this term is bigger than 0. I don't know what it is, but of course now I get here a lower bound. I get a lower bound on a quantity. It's important for bigness. And the lower bound that I can get a hold. Let's see. All right. So and now, of course, it follows immediately that we have a criterion for bigness. So bigness should have here H1 omega x full, and then it will be equivalent. But we don't have that. We have just a lower bound for it, and so I know that if the lower bound for H1 omega plus the second number plus the vector 0, then the cotangent bound is big. The good thing about this criterion is that it depends on topological data, which is easy to have, to understand, and from similarity data, which you, but if you have a construction, you know, normally in this question, the one question is to produce a surface of gel type with the cotangent model would be via construction, right? And in construction, you know the topology and you know the similarities. So you can know these, but we actually have a bigger theory behind it, and we'll see what happens. But so this is the good criterion in terms of being able to apply it. So this is the criterion we have. Now let's talk a little bit about finding these invariants. Okay. So finding these events is actually not so. It started in my paper with Fede, but we actually made a mistake. And this is actually a simple exercise after an exercise, but we made a mistake in the calculation, which actually allows us to arrive to the result via a kind of sophisticated duality argument. But I'll do this for later for comments on this. So so calculated invariant for H1, but it was corrected by Thomas. He found the correction of the invariant, and then there's also work of Bruno, Thomas, and Oliveira on surface with A1 C1. Then later on with my advice, we dealt with the case of AN singularity. There is also now also work of Bruno and Chu also proving some of the results. We'll see the results we have. So let's say something about these. I'll define the invariants quickly. So okay, so we are interested in surfaces with, for us, actually interested in canonical models, so surfaces with canonical singularities, AB singularities, any singularities are quotient singularities. So they live. So canonical models live in a bigger space of surfaces with isolated singularities, which are quotient singularities. All right. So so say Y is an objective normal orbifold surface. So I mean surface with isolated singularities, which are quotient singularities, and that X is minimal resolution. Then we have on X the smooth surface. We have the usual symmetric powers of the Cotangent bundle, but we also have a sheet on the orbifold surface, which is it can be described in many different ways, which is a reflexive shift. The rod is reflexive and power of the Cotangent bundle, which can be, for example, described as look at the symmetric power of the Cotangent bundle on the resolution and you push forward. That shift is not reflected, and then you do double dual to make it reflected. Otherwise, you can look at the symmetric. You can look at the shift on Y on the smooth points. Then it's the symmetric power of the Cotangent bundle, and then you extend that shift to the full line. All right, and well, if you study these shifts on X, on the resolution, and on the orbifold, we are dealt with having to compare the Euler characteristics of the shifts on resolution downstairs and understanding downstairs over here the samples. So you have the holomorphic Euler characteristic on resolution. It's related to the holomorphic Euler characteristic on the orbifold surface. And there's a correction term which is given by what's called the local Euler characteristics. So these that comes, they are singularity. They have to do with S is the singularities of Y. So this is the local Euler characteristics of the associated with the sheet, the orbifold sheet. And because we have these singularity invariants, but then you also have you could also try, well, if you have in this orbifold, now you focus on the orbifold, the Euler characteristics on the orbifold, and how do I what is it? Well, if it's smooth, it's described by the Bruno rock via this topological data, the Shem class of the symmetric power of the bundle, divided by the total class of X. Well, you can define the same classes for in orbifold case, but in that case they don't match. It's not the same. You need a correction term. So that's the other event of surface one needs. And then the other one is how I relate the topological piece for the orbifold surface with the topological part of Riemann rock for the resolution. Well, they don't match, of course. There is a correction terms involving the local orbifold or the characteristics of singularities. So we have all these things together, and if you now I should say something about this kind of. So what's the definition of the Euler? Well, we know that we want this to happen, but what is this? Well, this is going to be equal to H1, and it's right here. But then there is this, and it has to do. Remember, this has to do with what I want, because remember, I call it H1 omega X, the local singularity invariant I use in my criterion, it comes from here, because it's this divided by M cubed, and I do the limit, correct? The limit, and then it goes to infinity. So this is part I want to know. I really want to understand this. Because this is what comes to my invariant. And there is now a part here, which I call H/0 omega. And this has to do with what? This has to do with the symmetric differentials. So you look at a singularity, that is, you look at a neighborhood of singularity, you look at its resolution, and it has an essential locus. And I look at symmetric differentials on the resolution, which are defined away from the exceptional locus. And I want to know if I can extend them to the exceptional locus without acquiring singularities. And so these are the special differentials away from the exceptional locus. These are special differentials on the full. So I want to know how many. So basically, this is counting the obstructions to extend special differentials away from the exceptional locus to the full neighborhood of the exceptional. So right. So and you have this part here, which has to do, which is easy to calculate. So this is calculated, and this is what I want to calculate, but I cannot do it directly. I'm going to do it via this. This is the path. I will try to understand these obstruction spaces to extend special differential. So, okay, by the way, now I'm combining everything, because if you from these series of equalities, I obtain that this is equal to that difference. So, but since this is equal to that, and I write it this way. So, what I want to calculate, which is this guy, I can calculate it by knowing this invariant, that invariant, and this invariant. Okay. But this is very easy to calculate, so this is done. This is not so easy, but you can do it. But asymptotically, it's very easy. So this is can be done. It's like it's fast. Well, we calculate this for AH class, but in a sense, the technology is fast. So the real question is how to calculate this invariant, how to understand which differentials don't extend. Right. So that's the law of logic. So I just of course we are using in the asymptotic piece. So we want this, and let's just make here. So what's known from the past, known from since the 90s, that that this correction term here that we needed doesn't grow like M cubed, grows like actually like M. Doesn't so this asymptotic piece M cubed, this is 0. So if I want to look at this invariant, this part disappears. This part here is just the the local second number of the singularity, which is easy to calculate. It's not known since always. So basically, if I want to know this my invariant, the only thing that's not known is this invariant. I mean, if I know this invariant, I can figure out my invariant. Of course, so I'm just describing the strategy. All right, so that's it. So can you see the fundamental relation? So understand here. I'm just going to here reference what do we know about the second number, local second number of a canonical singularity. I know that C1 squared, the C1 squared is 0. The local second Sharp number is obtained by the topology of the exceptional locus. So the Euler characteristic of topological characteristic of the exceptional locus minus 1 over the order of the local fundamental group of my singularity. Okay, so these numbers are all known, those in the institute. Well, I'll guess it is. That's the result. So now the really okay. So what do we do with my students, Sergey and Weiss? We looked at AM singularities, and we are able to fully determine the space of obstructions to extend symmetric differentials. And we realize that the space of obstructions can be described as a polynomial weighted lattice sum over polygon. Polygons, the shape of polygons depends on n. N is the order of singularity, and m is the degree of symmetric differentials. And I write it here, and to give us a picture. So the result is as so if you fix n, then you change m, which is what we want to understand, right? We want to understand it's n, and m goes to infinity, and I want to do this over m cubed, and I want to do it. That's what I want to say. But actually, I can describe every single term. It's given by this weighted lattice sum, which we call its entire series. So basically. And the interesting thing is that these polygons change with them. They are not dilations, they are almost like dilations. I mean, they preserve the polygons, the shapes, the slopes of the limiting edges. And first of all, it's not like dilations. So we can have, there's an entire series of understanding these lattice, weighted lattice sums as a polygon kind of dilates. This is called a hard theory. And we obtain that actually this function of m, the function of m is a quasi-polynomial in m of degree 3. Quasi-polynomial means that if you write it down, the coefficients of the polynomial are periodic functions in m. But the first coefficient m cubed, is not periodic, it's just a period 1, that's period 1. The second coefficient also has period 1, and the other ones have the period. And I give an example here. For example, if you look at A2 singularities, I did it for A2 and for some other ones, not many, just for you to see how the, so you see that it's not a polynomial, it's a quasi-polynomial, right? So the leading coefficients are always the same, and that's the one I'm interested in. But anyway, if you ask me what's interesting to know these numbers, well, the interesting is so the leading coefficient is important for us for bigness. But if your question is, you will say you have say an hypersurface, and you know it has degrees something, so you know the second number, and you know it has some bunch of singularities. These numbers will be able to tell you the m numbers, not the single digits. If I'm going to know, there's the resolution of these singular hypersurfaces. Have symmetric differentials of order something, order like 10. Well, then you need to know these numbers. These numbers will allow you to tell you existence of symmetric of a given order. So that's the point. If you want to know that, and actually some people want to know these things. Here I have the shape of the polygon for an AC singularity. They look like this, and as m changes, this polygon remains the same shape. Come on, dilation. That's it. But okay, the most important thing is, so this now go for what really matters. So, which is that we obtain actually, okay, the question is, so we are interested in the leading coefficient. So this is a quasi-polynomial, and I want to know this guy. I want to figure out what this guy is. And we are able to do that for AM singularities. But I'll describe it for not H0, but for H1, which is the event I want. We got a closed form. So this we have a closed form for the invariants. For a while, we have a method, the method to calculate them. So if you tell me, I want to know the invariant for A10 singularity, and there was a method, and you go through the method and you get the number. But we actually, good thing about sitting on paper for a while, eventually I was able to figure out a way to obtain a closed formula, which is good because once you have a closed formula, you can do a lot of things that you cannot do with a method. Well, one of them is that we realize the following simple properties. That is invariant is always less than n over 6, and it is bigger than n minus 1, 6 over 6. So we have a good understanding where the invariant lies. This less than n over 6 is very important. So there's I guess there's a conjecture that this is also true for the other canonical singularities. So I'll say that H1 omega dn is supposed to be less also than n over 6. And also for the matrix. So, but I don't know. It's much, it's not trivial even for ANC lattice and for the other similarities to prove this. If someone has the courage, I encourage them to practice. But anyway, to find, I think maybe not super well, it's maybe doable to find a bound but it will be very tough to do to actually get the close form. Encourage anyone to do this. But anyway, we know this, we know that. We also observe that these properties is good for reasoning later on. And you also realize, this is important because if what we had in the past, if you saw this, we had that H1 omega an plus h bar omega an. This was equal to T2 log an over c delta. This was the version we had from before. And what it's saying is that as n grows, basically 100% of this comes from H1. Not from this part. In fact, this guy is bounded with n. So most of the local second set number of an n singularity, n is very large, it comes from H1. It's important for comparison with other criteria that are out here. I will this see how it's not how much time I have. But okay, here it comes. So after my work with Freddy, there was a very good work of Rousseau and Bruno, using the duality criterion that we gave in the paper. They extend our results work for normal singularities. They do for all canonical singularities, but I will say the same because our logic is carries through for all canonical singularities. And they obtain, they wrote in a completely different way. They obtain a criterion for bigness, and which, if I rewrite it in the language I put, the criterion that they have is that so the good of similarities for them is this one here. It's not by well, ours is H1, but but this difference is not. The reason to do this is because it falls from our quality argument that we couldn't figure out. We could figure out the contribution of similarities either from H1 or H0, and so this using this is like say you cannot calculate H1. What's the worst I can do, or the best I can do? Sorry, what's the best I can do? If I know H1 for contribution to H1 from similarities, this is it. So this is basically say I cannot calculate H1, I should use this guy. But if I can call it H1, I should do H1. And from this statement here, falls from AN singularities that by using H1, I can, the contribution from singularities can be close to the double from our criterion, because they divide by 2. And this is for if the surface has only one AN singularity and N is very large, this number is the double of that number. And that has a huge impact. Right. So anyway, so that's a comparison with the other criteria once you write it in the same form. And okay, let's continue. So let's see we'll see the geographic impact of this. Okay, so now if I have a criteria, if I have a criteria like this, and I want to understand how good is it. I mean, I need to understand what do I know about this quantity. So if I have a surface X and I know the shell numbers, do I know anything about the potential contribution from singularity? So of course this surface will have some canonical model and we can have some singularities, and therefore for the singularities I obtain some information about the H1, a lower bound from H1, and I want to know what can I obtain here. Now, if it's very large, then I'll have the information bundle. So that's the question. So how is there any control on the localized H1 from the shared numbers? Okay, so now I'm going to focus on really, I think those results are probably true for all canonical models, but I can only state them for canonical models which have AN similarities. So from now on, my rational class of surfaces is one for which the canonical model has only AN similarities. Okay, say the canonical model has K similarities, AN similarities, A1, correct? Okay, now what's important to know is, of course, I am going to define this number, rho minus log x. This is the number of minus 2 curves on the minimum model. Right? I mean, it's clear that if the surface canonical model has K singularities, and they are events, this guy here gives me n minus 1 minus 2 curves in the resolution. And this guy here gives me nk minus 2 curves in the resolution. So the minimal model, or if the surface canonical model has this singularities, is a surface which has summation when from I from 1 to k of ni minus 2 curves. Correct? So okay, now this is what we observed before. So this is what I said before. And now I observe here from so I have information about how to bound how to that from the results here I described upper bound, a lower bound on the H1 omega. So we can know something. So if I have from what I have wrote before, the localized H1 of rational class of surfaces is bounded above by the number of minus 2 curves on the minimum model divided by 6, and is bounded below by the number of minus 2 curves minus 1/6 the number of singularities divided by 6. So this gives me now an understanding of when do I have using my criterion, when can I use my criterion to get bigness, and when I cannot. So for example, follows this thing. So if I have a surface whose the number of minus 2 curves I have on the surface minus minus the number of singularities divided by 6. If this is bigger than minus the second number, then the canonical model criterion tell me that cotangent number is big. Right? If I know that the number of minus curves is less than the second number, negative, then I cannot apply my criterion. Criterion will not be enough. I mean, the localized H1 will not be enough to counterbalance. This is all about when is the localized H1 going to be able to add it to the second second number, when it's going to be positive. Yeah. So if you have this, then I have it. If I have this, I don't have it. But it's good. Okay, let's keep going. Right. Okay. So now the question is, how do I bound the number of minus two curves on a rational class? All right. So there is a Mioka bound. Mioka bound tells me that if I have a rational class, I have this amount to spend in similarities. And each similarity costs a certain amount of money, which is the localized second channel. So this way is a way that is basically bounding the number of bounding similarities on a certain rational class. If I have a rational class with these set numbers, I know that my similarities can only cost this amount, right? So, for example, this Malcolm bound matches perfectly, directly because the similarity contribution of Rousseau criterion. If you tell me that so this is bounding, of course, this remember the criterion had this and this 3 factorial and 2. This is also localized, the localized, conditional similarities to H1. So but I have a bound here, and of course, second number it comes from these numbers. So it's very easy to put them together, and it tells you that if I have so remember, like there is the geography thing. If I have here the line slope 3 fifths, if I have a pair of set numbers lying below the slope 3 fifths, the criterion will never apply. So I cannot use if I have a surface with set numbers below with slope below 3 fifths, the criterion will never show that the surface has been functional. If it's upstairs, maybe, but of course, remember, you never know. So if shell numbers, so being big is not only about shell numbers, and then of course you have to know the complex structure. But it's possible that if I have these shell numbers, that well, then there is a family of surfaces with those shell numbers. It tells me that maybe it's possible that in that family there is a surface will be functional. To know if there is a surface, we have to construct a surface. And then a surface whose canonical model has this amount of similarities, and then if you are able to show that, then you are able to produce a surface with the functional. But what's known for sure that if it's below that line, there's no way. Even if you have the best construction of surface with with canonical model with many similarities, that criterion will never be able to show bigness. Right. But okay, but now if you look at from our perspective, our criterion, I'm going to have to go now a bit fast. From our criterion, the Mioka bound actually it's not a good bound. Not a good bound. Mioka bound is very good at bounding similarities if similarities are all say nodes, the best thing. If it's nodes, meaning like the minus two curves come from a minus two curve comes from just one similarity. Right? If I have say an A10, you have 10 minus two curves coming from one similarity. And the different similarities you have, the worst is Mioka bound to control the number of minus two curves, which is what we get in our criteria. So, for example, if you look at the shell numbers of quintic hypersurface, the Mioka bound says that you can have at most 32 minus two curves if they come from nodes. So you have at most 32 nodes, which is pretty good because the bound is 31. So it's very close to the best, the real thing. But if you ask for level bound to bound number of minus two curves that can occur on a surface with the shared numbers of a cubic surface, the bound will be 52. Meaning it will allow a similarity of type A52. It doesn't prevent it. So it's good. So it's good to bound curves if they come from individual singularities. From singularities for only one minus curve, like A1. Now there's another bound, which you go quickly, which is the bound coming from Orchard, simple bound Orchard, which bounds Orchard bounds H11 of the minimum model. And that of course bounds the Picard number of the minimum model, which bounds the number of minus two curves. And that bound actually is stronger. It's stronger to bound minus two curves because if you look, for example, for the quintic hypersurfaces, the Hodge bound says that you have at most 44 minus two curves, which is less than 52. So you see that the Hodge bound is stronger about bounding minus two curves. Anyway, if you do that, I'll go quickly. We realize that for our criterion, if you use a Yoka bound only, our criterion could be applied to all pairs of shared numbers, except for finitely many. The shared numbers, the pairs which have C1 squared equal to 1 or 2. So it's actually, but with the Hodge bound is a stronger bound, and that tells us the following thing, that our criterion cannot be applied below slope 1/5. So let's go to maybe. So the Rousseau criterion has come slope 3/5. Anything below here cannot be applied. You know, there's no surface with these shared numbers for which the contribution from the similarities on the canonical model could counterbalance the negativity of the second set number. For our criterion, here that's not a problem. The problem is if you go below 1/5, which indicates that the conjecture is that, and then I'll leave it to questions, because this I'm moving probably at half of the talk. So the conjecture is this one, that for surface of child type, the cotangent model is big. The slope has to be above 1/5, and you have examples going up to 1/5. But below 1/5, we conjecture that the cotangent model is not big. In fact, we conjecture that below slope 1/5, there are no separate functions. It's stronger. So, but the conjecture is that one. Now, I will get. So you could say, what are the examples to prove this conjecture? So I will use conjecture from the perspective of our criterion. Our criterion cannot be applied below 1/5, so there should not be anything below slope 1/5. But do we have examples to demonstrate that? Yes. For hypersurfaces, we can go pretty down. We can show that our hypersurface of degree 8. There are deformations of hypersurface of degree 8 with big number. That's the lowest degree you can do in the question I put earlier on. For degree 7, we cannot know, but we think it's possible. Some things for that time. For degree 6, it's the borderline, because our criterion asks that if I ask for the existence of 85 minus 2 curves, and the Hodge bound tells me that if I have a surface with shared numbers equal to a hypersurface of degree 6, the maximum amount of minus 2 curves possible is 85. That's the number I need. So, but I will have to produce an hypersurface in P3 with similarities. For example, having an A85 similarity. I don't know how to produce such a surface, but if you could do that, we will prove the existence of such a surface. For degree 5, it's impossible. It's below our scope. Okay, and then we have examples where simple connected surfaces with slope very close to 1/5, which are Nicolas bundle, coming from double covers of P2 branch along the singular curves with AB singularities. And finally, just that, so and then the slope is we get slope of I think 25/107, close to 1/5. That's with a P1x equal to 0, so regular surface. But if we consider irregular surfaces, we can show that actually we can go up to slope 1/5 via construction of the bar. We can go all the way to 1/5. So in a sense, we have part of projection shown that I know that alpha, the alpha, the even of all slopes with the model is at most 1/5. But if it will go below 1/5, that's conjecture. We say no, that's complex.